We will now look at how to express CFTL specifications using Python code, with the intention of allowing software engineers to easily express their behavior requirements. The specification library that we provide is the first interaction with VyPR that a software engineer has. It's a translation from the mathematical formalism that is control flow temporal logic to a structure that can be used by VyPR during instrumentation and at runtime to check whether the specification given actually holds. So with this in mind, it's vital that first, software engineers can easily express their requirements using this library, and second, feedback to mistakes in specifications is useful. For example, if an engineer accidentally compares a numerical value to a string, then they need to be told. The library that we provide to allow engineers to convert their CFTL specifications into Python code is called PyCFTL. And you see here the first example of a translation from the CFTL formalism into Python code. So here we have a single quantifier, and then the innermost quantifier free part of the formula just performs a simple duration comparison on the variable given by the quantifier. And this is translated into Python using the PyCFTL library, first by converting the quantifier into the for all syntax you see here, where we also use Python's keyword argument feature to implicitly define the variable t. We then express the innermost quantifier free part using a lambda expression. So for example, here we have the variable t, and in the original CFTL version we used a duration operator to measure its duration. The equivalent in PyCFTL involves taking the variable t, which we assume contains some representation of a function call derived at runtime, and calling the duration method on it. We can then use Python's standard comparison operators, here we have less than, and write a very easily readable piece of code that clearly encodes the fact that we want the duration of whatever function call is held in t to be less than 1 unit of time. As another example, we take the CFTL formula that we saw before with implication and show how in PyCFTL we can use the if-then syntax to encode our implication. We then treat the variable q as a state because it's a concrete state, and first refer to the value that it gives to a variable x and ask if this is greater than 10, and then we also refer to the next function call along by using the next call method defined on it. Now significantly we see that once we've used this next call method, the result of that will be a transition, and as you saw in the previous slide, transitions define the method duration so that we can measure how long they took. So in this case, we start with q, we ask for the next call of the function calculate something. This gives us a transition on which we can call the duration method to obtain the time that that transition took. And then we can use the standard comparison operators that Python provides. Finally, we see how to translate the time between operator into PyCFTL. And as can be seen here, there's almost no difference. In fact, in this case, the PyCFTL code gets slightly more intuitive because instead of having this dest operator that's present in the original CFTL version, now we have this variable t that holds a transition, and we can call the method result on it, which gives us the concrete state immediately after it. So to conclude this brief introduction to PyCFTL, we provide an intuitive library to software engineers so that they can express the behavior requirements of their programs in an intuitive way and in a language that they're already accustomed to. Because of the way that PyCFTL is implemented, that is, it overloads most basic operators on its objects to allow a cleaner syntax, we also have the advantage that we can provide useful error messages. For example, in this specification, we capture all of the transitions that are calls of the function calculate something, and then we measure the duration, but then we compare that to a string. So this is clearly not a correct specification. Because of the way that PyCFTL is defined, we can detect this and give the error here that you see. We're now going to address the problem of how to extract the data from a program run so that a given CFTL specification can be checked. We call the problem of determining which parts of a program from which we need to take data to check the satisfaction of a CFTL specification the instrumentation problem. And the solution to this problem begins by saying that, given a dynamic run, one of its concrete states is relevant if the corresponding symbolic state was identified by instrumentation as being needed to decide whether or not the given CFTL formula was satisfied. In general, our goal is to reduce the number of concrete states that are in a dynamic run which are not relevant with respect to a given CFTL specification. The major consequence of solving the instrumentation problem badly is that there will be more overhead at runtime because the monitoring algorithm will spend more time working out whether it really needs some of the data that's been observed. On the contrary, if the instrumentation problem is solved well, then the monitoring algorithm can have confidence that the information it's getting at runtime is mostly needed. First, we need to define the instrumentation problem formally. To do this, we first take an example CFTL formula because instrumentation takes place with respect to one of these, and then we say that the instrumentation problem involves determining the set of symbolic states such that a dynamic run containing only relevant concrete states with respect to those symbolic states contains enough information to decide whether the CFTL formula holds. This is just a slightly more formal expression of the notion that we discussed in the previous slide. So ultimately, we have to completely remove from the dynamic run in question any concrete states that correspond to symbolic states that instrumentation determined were not useful with respect to our formula. For example, in the case of the CFTL formula on this slide, we have first of all that we want to capture concrete states which change the variable a, and then we also know that we want to capture transitions that were calls of the function calculate something. Now, by looking at this formula, we know that these are the only two variables or functions that we care about, so anything that doesn't involve these we don't have to instrument. To describe our approach to the instrumentation problem, we first have to introduce some new terminology. So here we have an example CFTL formula, and as we've already mentioned, we have quantifiers and we have variables. But then, when we look at the structure of the innermost quantifier-free part of the formula, we have two new terms that we have to introduce. The first of which is an atom, and these are the parts of the formula that would be leaves if we were to look at the syntax tree of the formula with respect to the Boolean operators involved. The next new term is the subatom, which comes into play when we consider atoms that take measurements at two different points in runtime. For example, in this case we have Q and dest of C. So Q forms one subatom, and dest of C forms another. Notice that we only refer to Q as a subatom and not C, and this is because the intuition behind subatoms captures the final concrete state or transition that's given to an operator. If we then zoom into the structure of a CFTL formula further, we can define the set of base variables of an atom. So in this case we have what we call a mixed atom, and as we saw before, we have subatoms Q and dest of C. But these two subatoms are based on the variables Q and C. So when we think about the set of base variables of an atom, we mean the actual variables from the quantifiers that we used to derive the concrete states or transitions used by that atom. When we perform instrumentation, the output of our approach is a tree which we call H5. This tree will help us to organize our instrumentation data in such a way that it can also be used to optimize the monitoring process. Our first step in constructing the tree H5 is to inspect the quantifiers of a given CFTL formula. So here we have an example with two quantifiers we have highlighted in purple and blue, and the first quantifier looks for concrete states that are changes of A. And as we saw before, for one of these predicates to identify a concrete state, this means that the symbolic state associated with that concrete state has to indicate that A could change. So in this case it makes sense that the vertices in the symbolic control flow graph on the right that contain the letter A should be highlighted by instrumentation. Further, for each such vertex that indicates a possible change of A, we have to reach forward in the graph to find pairs of symbolic states whose second symbolic state indicates a call of the function calculate something, and this is how we determine the parts of the symbolic control flow graph that would correspond to the second quantifier. And once we've performed this traversal with respect to the quantifiers, in this case we would get a set of pairs, which we call static bindings. Formally, each of these static bindings is a map from variables from the CFTL formula to symbolic states or edges in the symbolic control flow graph. Finally, we denote each of these static bindings by beta, and highlight on the symbolic control flow graph on the right here a subset of the static bindings that would be derived with respect to this specification. And now that we've defined static bindings, we can introduce the first level of the tree H5. In particular, this level of the tree consists of the static bindings derived. Now, if we look at the symbolic control flow graph shown on the left, it's clear that more than 3 static bindings can be derived, but we just show 3 here for the sake of illustration and to save space. The next step in instrumentation, once we have static bindings, is to inspect the atoms and the subatoms of our CFTL specification. So as we saw before, time between less than 0.5 makes an atom, and Q and dest of C makes subatoms. Atoms define the type of measurement to take. Here the atom is time between, so we will clearly need to measure 2 timestamps. And subatoms define where to take the measurements. In order to determine where to take measurements, we have to translate each atom to have meaning in the symbolic control flow graph. We call this lifting and define the lift function to take a subatom along with a static binding. The intuition is that from a static binding we can take a symbolic state or an edge from the symbolic control flow graph, and then we can use the subatom to determine the kind of traversal that we have to do from the given point in the symbolic control flow graph. By performing this traversal, we then determine the parts of the symbolic control flow graph to which the relevant concrete states that need to be in our dynamic run must correspond. Here we illustrate the process of taking a static binding, in this case beta 1 and beta 2, and lifting the subatom dest of C according to that static binding. So the subatom that we've been given is based on the variable C, so we will care about the value to which the static binding beta 1 maps C. In this case, C is mapped to a pair of symbolic states or an edge in the symbolic control flow graph. And we know from the subatom that we have that we care about the destination of that edge, which is the vertex that indicates a change of the variable result1 and call of the function calculate something. We perform the same process below for the bindings beta 2 and beta 3. It's exactly the same idea. So ultimately, by applying this process in generality, from a given static binding, we can break apart the structure of the innermost quantifier free part of a CFTL formula and determine all of the parts of a symbolic control flow graph that are relevant to each part of the innermost quantifier free part. Ultimately, we can summarize this process in terms of an algorithm. So for each static binding that we derive, which we call beta, and then for each atom or subatom alpha, we compute the lift function given alpha and beta. The result of this algorithm is the tree, H-phi, whose first level is static bindings and whose second level is atoms. The leaves of this tree are then necessarily the symbolic states or edges from the symbolic control flow graph that have been deemed relevant by the instrumentation algorithm. By organizing the results of the instrumentation algorithm into a structure like this, we make the instrumentation information useful to the monitoring algorithm. We will see precisely how this works later on in the tutorial. In order to demonstrate exactly how instrumentation works, we've built a visualization tool that allows us to replay real runs of the VyPR tool. So this is our visualization tool for the VyPR framework. This screen right now is the instrumentation screen, and at the top you see we have a set of events that happen during instrumentation. So we begin with the first event that signals the beginning of a function being processed, and then we have the events for a new binding, a binding being completed, another one, and another complete binding, and then the final events for determining the actual instrumentation points with respect to those bindings. And this is the symbolic control flow graph for the code that we monitored in this case. So if I now begin to scroll through these events, you can see that when I click next, first of all for a new binding, I get the variable that I care about in the specification, and then I get the point in code that's been identified, and I get a new binding on line 9. If I then go to the next one, I see that the binding was completed because there's only one quantifier here. And then if I go to the next event again, we see that we're on this quantifier again because, again, there's only one quantifier, but in this case we've seen another line, another statement in the code where what happens at runtime satisfies our quantifier is captured by it. So here you see line 15 appear here in the binding tree. So when I click next, I see that this binding is again completed because only one quantifier. And then I go on to finding all the set of instrumentation points. So for binding 0, which is line 9, you can see that we only have one atom. We have one atom that has multiple subatoms, so we have S and the next call of calculate something along from S. So I have just this one atom, but then I have the left-hand side, which is S, and I have the right-hand side, which is this next call of calculate something along from S. So for the left-hand side, you can see that I have line 9, and of course I have the change to A, which is identified by the quantifier. But then for the right-hand side, which is the next call of calculate something, I have line 10 and line 11. So we care about line 10 and line 11 because this is where the transition actually happens. So if you look at the specification, we have s.next call of calculate something dot result. So what we really care about is the state immediately after it, but we need to know about the transition itself, and the transition itself happens starting immediately after line 10 up until immediately after line 11. However, we only care about what happens immediately after line 11. If we go on to the next event, we see something similar, where we have line 15, which corresponds to the change of the variable A, but we also have line 15 to 16, which is the next transition that satisfies the right-hand side of the atom. And we do the same thing here. So the transition actually happens between the end of line 15 and the end of line 16, but because the specification is asking for the result, i.e. the state immediately after it, we only care about the state immediately after line 16 has been executed. Now, this instrumentation tree is what we showed earlier, and this is the first thing that is constructed by the instrumentation process. So you see that the first level is the bindings, the second level is the atom indices, the third level is the atom subindices, so we have the left-hand side and the right-hand side here, which corresponds to subatoms S and S.next call. And then the leaves are the parts of the symbolic control flow graph that we care about. So in this case, in the visualization tool, we care about the actual lines because it makes it easier for users to see. Once we've constructed the tree H5, we see that there's some overlap between bindings. In particular, in this case, we see that the vertex with the variable change result 3 and the function called calculate something, and the vertex with the variable change A is repeated across multiple bindings. When it comes to actually placing instrumentation code in the target program, this overlap will translate into repeated measurements and ultimately unnecessary overhead. So our next step in instrumentation is to eliminate this overlap, thus reducing the chances of unnecessary overhead. By inverting the instrumentation tree that we construct to map symbolic states to bindings, we can place only one instrument per critical symbolic state, thus avoiding repetition and reducing unnecessary overhead at runtime. The final stage of instrumentation is to actually place the instrumentation code in the target program. To do this, we take advantage of Python's intermediate bytecode representation of programs. In particular, normally, execution of a Python program involves reading in a source file, which is .py, converting that to bytecode and then interpreting the bytecode. This bytecode can be made persistent in PYC files, which are essentially compiled Python files, and these can be executed without the need for conversion from source to bytecode. The instrumentation process performed by VyPR generates Python bytecode rather than Python source code. We're now going to take a brief look at what this involves. Given Python source code along with Python's standard library, it's easy to derive the abstract syntax tree of the program. Once the abstract syntax tree is obtained, we then map parts of this tree to the symbolic control flow graph obtained by analyzing the source code. Using this relationship, along with the output of the instrumentation algorithm over the symbolic control flow graph, we can determine which parts of the abstract syntax tree of the program we need to modify in order to insert instrumentation code. Once we've performed this modification of the abstract syntax tree, we compile it to Python bytecode and write that to a file.